Alright guys, welcome to this particular question here. Alright, so this is part B of that question I gave you yesterday. And so what you're trying to do is you're trying to get the coordinates of Q in terms of this angle theta here. Now, as a bit of a clue to start with, okay, what I've done here on this diagram, I've represented P here, and we've got also Q. Now, I've drawn an angle alpha here, and what you could do as a bit of a clue for this question here, you know that the line from O to P, let me put that point O in there. Okay, the line from O to P and the line from O to Q are at right angles to each other. Now, what does that mean? Well, one of the things it means is that when you multiply the gradient of the line from O to P, so the gradient of the line OP multiplied by the gradient of the line OQ would be equal to what? If they're at right angles to one another, and you're told in the question that they always are. Well, that would be -1. So if you're able to get an expression for the gradient of the line going from O to P in terms of theta here, okay, and a big clue for that is that you've got the coordinates of point P as A cos theta, B sin theta, so you can use the change in Y over the change in X to get an expression for the gradient of the line O to P. Now, try and get an expression for the gradient of the line going from O to Q. Now, the coordinates of Q will be similar to this, but you're using a different angle. Okay, and then use this idea that those two gradients multiply together to give -1. Okay, I think that's enough of a clue. So I'm going to pause the video here, see what you can do. Okay, get an expression for the gradient of OP in terms of theta and the gradient of OQ in terms of this alpha here. Okay, then multiply them together to get -1. Okay, and then see if you can then get, see if you can then somehow get something involving this angle here, perhaps the tan of that angle, okay, in terms of this angle theta here. Alright, so pause the video, see what you can do with that clue. Alright guys, so welcome back. Let's have a look at trying to do that then. So what I've got is the gradient of the line going from O to P. Let me see if I can fit it in here. Should be able to. OP. Okay, I'm just going to use the change in Y over the change in X. So that would equal B sine theta over A cos theta. Okay, which will be B over A tan theta. Now, if you think about the coordinates of point Q, let me just put it here. So Q would have the coordinates A cos alpha, B tan, sorry, not tan, sine alpha. So you can get an expression for the gradient of OQ in exactly the same way as we did above here. So this will be B sine alpha over A cos alpha, B over A tan alpha. Now if you multiply those two gradients together, so the gradient of OP times the gradient of OQ would equal B over A tan alpha times B over A, theta there, and tan alpha here. And we know that when you multiply those two gradients together, because they're at right angles to one another, that will equal -1. Now what I want to do is I want to get tan alpha on its own here. So multiplying b over a times b over a, that would be b squared over a squared. Okay, let me do this in 2 steps. So that would be -1 over b squared over a squared, which will be -a squared over b squared. So tan alpha would equal this divided by tan theta, which will be -a squared over b squared times 1 over tan alpha, theta. So which will be -a squared over b squared times cotan theta. Alright, so that's an expression for the tan of alpha. So let's move to a new page. Let's consider that in terms of how we might be able to represent this information on a right angle triangle. So let's make a new page. So we've got the tan of alpha was equal to -a squared over b squared times the cotan of theta. Now remember, cotan is simply the inverse of tan, so we could actually write this as -a squared over b squared. Now remember that tan is sine over cosine, so cotan will be cosine over sine. Now I want to represent this information here, that the tan of some angle, in this case alpha, is equal to this over this. Now if you represent that information on a right angle triangle, remember in the what we did at near the beginning of this question, we use change in y over change in x to represent the gradient. So what we're going to do here is basically reverse that and make ourselves a right angle triangle where this will be the opposite side and this will be the adjacent side. Okay, and then what we can do is we can then get an expression for the we can get an expression for the coordinates of point Q, okay, in terms of theta, as you'll see. Right, so let's get ourselves a little right angle triangle. Let's try and draw that neatly. So let's get myself a line here, horizontal one, that will do, and a vertical line here, and a line joining those. So if this is our angle alpha, then this would be the opposite side. Now this is a length here. Now this simply indicates a direction. Okay, so this length here would be a squared cosine theta, and this would be the change in y over the change in x here, so this will be this distance here. Okay, and so what we can do is we can get the length of the hypotenuse, okay, which will be this squared plus this squared, so a to the power of 4 cos squared theta plus b to the power of 4 sine squared theta. Now remember that the coordinates of OQ, okay, that length OQ, so the coordinates of Q, chord of Q is equal to a cosine alpha, b sine alpha, and what we can do is we can get an expression for the cosine of alpha and the sine of alpha using this triangle now. So I'm just going to put that up here. Just get a line separator here. Okay, so what we can say then is that the cosine of alpha is equal to the adjacent over hypotenuse and the sine of alpha would be this a squared cosine theta over that same denominator. Okay, so therefore the coordinates of Q in terms of theta would be, okay, so A, coming back down to here, A times the cosine of alpha, so that would be A B squared sine theta over this big long square root thing again. Comma, and then the that's the x coordinate, and then the y ordinate would be b times sine theta, sine alpha, sorry. So we're going to get b a squared cosine that, and then over this big long square root thing again. And there we have the coordinates of Q in terms of theta. Okay, all right. What would I like to point out about that particular question? I suppose the key ideas are, once again, that the coordinates of a point on an ellipse can be given by these parametric equations, and that is true if the angle here is acute, and also if you've got this other angle on the other side here, we can still get the coordinates of the point, say the Q here, in terms of this acute angle here. Okay, so that's a key point, and then the fact that the two gradients multiply together to give -1. Yeah, once you've got that, okay, then you're basically on the track. The tricky thing then is to realize that the tan of this angle alpha, once you've got it here in terms of A and B and cotan theta, is to realize you can represent that information on this triangle here, okay, and work from the gradient, which is given by this, back to this triangle here, and getting an expression for this hypotenuse, then to get the coordinates then of Q. Once you've got that, then it's simply a matter of replacing cos alpha and sine alpha in terms of these sides here, which are in terms of theta. All right, okay, so okay, I'm going to move on to the second question. I'm actually going to put that in a separate video, so I'll catch you there perhaps.